Okay, so we're going to learn to draw Lewis structures. These are covalent compounds. Okay, so what does covalent mean to you? Okay, they're going to be sharing electrons, very good, between what kind of elements? Nonmetals, yeah, very good. Okay, and so what we're doing is we're trying to represent the best we can a structure, so a drawing of a molecule. And we're going to start simple, of course, especially for most of you, this is the first time I'm doing this. There's quite a few rules we have to go over first. So this might seem a little overwhelming, but the best way to see these rules is to practice. So at first they may not make much sense, and then when you actually start to practice these, they start to make more sense. Okay, the first rule, and I've mentioned this, vaguely, is the octet rule. And this states that our representative elements, which means these are our group A elements, right? We all know where those are. Okay, they want to have a noble gas configuration. So everybody in here, we've heard that, right? Everybody has. Okay, but this means that all atoms besides hydrogen are going to want to have how many electrons, do you think? If it's the octet rule. 8. Yeah, they're going to want to have 8 electrons around them to be stable. Okay, but hydrogen, it's in that first row. How many does it need to be stable? 2. It needs to gain 1 and have 2. Okay, so it's going to be our only real exception. Okay, a Lewis structure shows the valence electrons. Okay, so when you drew a Lewis dot and you represented maybe nitrogen, and when you drew the symbol or wrote out N, that meant all other electrons that are in the inner shell. Okay, but you would put around there the valence electrons, which would be 5 for nitrogen because it's in group 5 on your periodic table. Okay, and so that's the same idea here. We're not going to show all the electrons. Okay, the only time we did that was in our orbital diagrams when we kind of drew them and went all the way up and drew everything. Okay, the valence electrons are the only ones we're concerned with. Anybody know why that would be? Why aren't we concerned with all the other ones? Yeah, they're the ones that react. They're the ones that are available, okay? And so they're in the outer shell, so they're going to react and collide with other atoms, okay? We first need to distinguish between bonding and non-bonding, and this is pretty, simple to see, but just to show you, okay, these are also called lone pairs. There's actually 2 lone pairs on oxygen, okay? And we're going to see how to draw this. Most of you, if you saw H2O and you were going to draw it, you'd probably leave off the lone pairs if you didn't know any better and you hadn't taken chemistry or hadn't had this class. Okay? So these are non-bonding electrons, simply meaning they don't bond to anything else, right? Okay? These are bonding electrons. Okay? Does anybody remember how many electrons are in a bond? 2, yeah. So if you count around oxygen, how many electrons does it have? 8. You always count, so you have 2, 4, 6, 8. Okay. Does that satisfy our octet rule? Yeah. Okay, what about hydrogen? 2. And earlier I said that hydrogen only wants 2, right? Okay, so with saying that, whenever you have a hydrogen in your molecule, which you may not, depends on what the molecule is, okay, it's never going to have lone pairs on it because it does not want extra electrons, okay? That is one of my pet peeves and that I say over and over again. The only way you're going to see hydrogen is with a single bond to another atom, okay? It can't double bond, it can't have lone pairs, nothing, because all it can have is 2 electrons around it because that's all it wants. It's never going to have more than 2. Okay, so we have a method that we follow, and I find this to be really a great way to bookkeep your electrons. That's all you're doing. Okay, and once you do this method, the NASB method, then you have kind of an idea of what your structure should look like instead of just trying to guess and move things around. And that's how I was taught. We just had to kind of guess and try to move stuff around and try to get the octets full, and then didn't really have much to go by. So this method, I don't even know if it's taught in your book. It may be. It used to not be, but the updated version it might be. It's great. It works even for my organic students. The first day of class, I hand them a Lewis structure sheet, and it's just like the one that is posted on Blackboard for you guys, and I say, here you go, make sure you can do Lewis structures, and we talk through it if they can't. And we go back to this. Okay, of course, with very large molecules, this method it still works somewhat, but it's harder to use. Okay, but you're going to be doing pretty simple molecules, so it works really well. So you're going to kind of set up an N, an A, an S, and B. So we got to talk about what those letters stand for. Okay, N is for needed. Okay, this is how many electrons does an atom need. All right, this is pretty simple, sometimes forgotten. Okay, all atoms that we're going to be looking at need 8 because we need the octet rule, right? We need 8. Okay, besides what atom do you think? Hydrogen, exactly. And it always needs 2. Okay, so that's going to be the same. It doesn't matter what column, what group, what anything, an atom's in. Okay, if any atom, you're going to add those up, how many ever atoms there are, and it's going to need 8. Okay, except for hydrogen. All right, available. Okay, A for available is the same thing as valence electrons. Okay, so we know what can we do to find the valence electrons. Look at the periodic table and look at what? The group number. Okay, so for our representative elements, okay, the group number is the number of valence electrons, right? Okay, so if you look at oxygen there, okay, what group is it in? 6. Okay, so in the needed column, you would have 8, but in the valence column or the available column, you would have 6, right? Okay, I'm going to pass these around just in case. Take one and pass. Okay. S is for shared. So this tells you how many electrons are shared in bonds. Okay? So all you're going to do is take needed minus available to give you S. Okay? This always has to be an even number that you get here. Okay? If you get an odd number, then you calculated wrong. Okay? Why do you think that would be? Why do you think it has to be an even number? Yeah, there's 2 electrons in a bond. So if we're looking at bonds and sharing, we're going to have an even number because there's 2 electrons in every bond. Okay, S and B, they go together. You don't always have to do B. I'll go ahead and do it. But whatever you get here for shared, you can divide by 2 because there's 2 electrons in every bond. And so then that will tell you the number of bonds that you're going to have, which is very, very useful, okay? Keep what? Yeah. Okay, here's some more rules, and like I said, these rules really, once you start practicing on your own, you can come back to this slide and kind of help you just, guide you through if you get stuck. Okay, but we're going to go over them anyways, just so we hear them once, and then you'll hear them over and over. Okay, if you have an ion, okay, and this means that it's not neutral, your compound's not neutral, okay, you're going to add or subtract an electron depending on if it's positive or negative charge, okay, and you're going to do this in the A column of your NASB method. Okay, everybody underline that or write that down. Okay, it's a common mistake to try to adjust for an ion in the needed. Okay, needed never changes. It's always 8 for every atom or 2 for hydrogen. Okay, so if you have a plus charge, what do you think you're going to do in your available column? Are you going to subtract or add an electron? Subtract, exactly. If you have a negative charge, that means your compound gained an electron, so you're going to add an electron. Okay. A lot of times you're given, a compound and you have to decipher what atom's going to go in the middle. So I'm going to have some bonds coming off of it. Okay. My best rule is that the least electronegative atom goes in the middle. Okay, so not the most, but the least. Okay, so fluorine is our most electronegative, right? Okay, so whatever is further away from fluorine. Okay. Another tip, carbon. If any of you go on to take organic, we'll do lots with carbon. Carbon always makes 4 bonds, and it's always in the middle. It likes to be in the middle. So if you have a carbon, it's going to be in the middle. Okay, so once you decide this, so let's look at water. So we've got H2O. All right, we already saw the structure, but we want to see how we get to it. Okay, so we're going to add up our needed. Okay? You have to add these electrons for every atom. Okay, so if we look here, we have 1 oxygen, so it's going to need 8, right? And you add here. You add them up. You don't multiply them or anything. All right, we have 2 hydrogens. Okay, hydrogens need how many electrons? 2, but you have 2 of them, right? So you can either think of that as 2 plus 2 or 2 times 2, whatever you want to think. So you can think 2 times the fact that you have 2 hydrogen atoms. Does that make sense? Okay. Everybody agree with 12 there? Okay. Available is the valence electrons. Okay, so what group is oxygen in? 6. Okay, what about hydrogen? 1. Common mistake on accident, students put 2 here. Okay, it's not in group 2, it's in group 1. Okay, they just think about how much it needs. Okay, but hydrogen has 1 valence electron. Okay, so we have 1, and then we have 2 hydrogens, right? So available, we have 8. Okay, once you draw your structure and you have it all drawn out and you've shown all your electrons, how you can check yourself is whatever you represent in your Lewis structure, if you have 8 valence electrons, then you should have 8 here. They should match up. Okay? All right, for S, this is shared. We take 12 minus 8. So that's 4 shared electrons. Okay, so if 4 are shared, how many bonds is that? 2, because there's 2 electrons in every bond. Okay, so a lot of times I like just looking at B. So I take 4, divide it by 2, and I get 2 bonds. Okay, the least electronegative atom goes in the middle, except for hydrogen. Because remember we talked about it? It does not want to have lots of bonds. It wants 1 bond. It is never central. Okay, so hydrogen is never the central atom, never has lone pairs, and only forms 1 bond. Okay? All right, so if we just have 2 atoms here, and we know hydrogen never goes in the middle, then who's going to be in the middle? Yeah. Okay, and conveniently here, we have 2 bonds. We said we have 2 bonds, right? So, okay. Another common mistake, and it seems a lot of students will kind of laugh at it, but it really happens a lot, is your formula here is H2O. So that means in your structure, you should have 2 hydrogens and 1 oxygen. Okay, when things start getting more complicated, students will want to just start throwing atoms in there. So if I give them, NH4 plus, and they start making, 5 hydrogens, or so always go back and make sure that you didn't try to add atoms in there that weren't in the formula. Does that make sense? Okay. All right, so you have 2 bonds. Okay, but we're not done yet. But we do have this. We can check this off. We have 2 bonds and 4 shared. 2, 4. Okay, but we haven't checked this off yet. So we're going to come back and do that. Okay, so once you've determined the central atom, And you can try to draw your skeletons, what we call it. So we haven't put any lone pairs or any filled up our octets. Okay? It says, that's what we did here, place shared electrons in the skeleton. So we made our bonds. Okay? That's what we already did. Okay? Then place additional electrons in the skeleton as unshared lone pairs. So basically this says you fill the octet of the atoms that are there. Okay? And you're going to start on the exterior. Okay, so whatever's kind of branched off from your central atom, you're going to fill in the lone pairs. And then if you still need more electrons, then you're going to have to put those on the central atom. Okay, so we'll practice this. This one's not a good example of that. Okay, and then you go back and you look at your Lewis structure, and the electrons you represent should equal the electrons here. Okay, so if you look at this second point, it says place additional electrons in the skeleton. Well, in the surrounding. Well, we know that we can't do that to hydrogen, right? I told you we cannot have lone pairs. It wants one bond. Hydrogen wants one bond. So it's happy like it is. Okay? But we know that we only have how many electrons represented right now? 4, but we need 8. Okay? And since hydrogen can't have lone pairs, so we've been to our skeleton, we can't add electrons, so we're going to go to the central atom and add them. Okay? And so we add a lone pair here and there. Okay? Now we have 8. We can check that off. If you count around oxygen, we have 8, which fulfills the octet rule. Hydrogen has 2. Everyone's happy. This is the structure. Okay? Okay, if we did, these are simple ones, but just to show you, okay, especially here. So if I was new to chemistry and you told me nitrogen, which is what our atmosphere is mainly composed of, I'd just probably draw a nitrogen bonded to another nitrogen with a single bond. Okay? But actually, it's a triple bond. Okay? So we're going to go through the NASB method so you can see this. Hopefully, if my thing will work. Okay. Okay, we have a diatomic molecule, meaning an atom that's bonded to itself. It's obviously a covalent bond because they're nonmetals. Fluorine is a nonmetal. Okay, if we add up the needed electrons, we have 2 fluorines that each need 8, right? Everything needs 8 except for hydrogen. So we need 8 plus 8, or 8 times 2, however you want to think of it, 2. We have 2 fluorines, so 8 times 2. Okay, and that E negative is just the electrons. Okay, available fluorines in which group? It's a halogen, so it's in group 7. Okay, and we have 2 fluorines. We've already said that. So we have 14. To get shared, we take N minus A. So we take 16 minus 14 equals 2 electrons that are shared. So how many bonds is that? It's just 1, yeah. So if we take 2 divided by 2, we get 1 bond. Okay? Which is perfect, right? We look at fluorine, and we have 2 atoms. We just bond them together. Sorry, that F looks a little crazy, but it's hard to fix. Oh dear, now I can't get my pen back. Okay, but we're not done, right? Because how many electrons have we shown here? 2. And we're supposed to have how many? Not 16, how many? 14. Remember this right here? That's our main focus. Okay? So we need 14 electrons shown. So at this point, we don't really have a central atom because they're just two things bonded to each other in a single bond. Okay, so we could argue that either of them was central. Okay, but we're going to go around, and that rule says to fill in the octets. Okay, so we're going to go around and give fluorine 2, 4, 6, and then there's its 8 in that bond. And then we're going to do the same thing to the other one. All right, so if we count around, 2, 4, 6, 8, 10, 12, 14. Everybody see that? All right, that matches up. We have one bond, 14 electrons, and there you go. There's the structure. Okay, if we do the same thing for nitrogen here, okay. All right, how many needed electrons are we going to have? 16, just like we did. Yeah. Okay. Now here's the difference between the fluorine and the nitrogen. How many available nitrogen electrons do we have? 10. Okay, because nitrogen's in group 5. And then we have 2 nitrogens. That looks like an S. Sorry, that's a 5. So that gives us 10 electrons. That looks majorly like an S there. Okay. 16 minus 10 is 6 shared. And when we divide 6 by 2, we get 3 bonds. Everybody with me? This is where finding the number of bonds is very crucial and a very big piece of the structure. Because like I said, I would have thought just a single bond between the two, and that would be that. Okay, but there's actually a double bond. A triple bond. So if you end up and you do this right here, okay, and you only have, one bond there, but you look down here and you know that you have 3. Okay, there's no other bonds we can make. So this is really a common mistake. You may laugh, but people will do this. Okay, why is that wrong? Because that is N4, which doesn't exist, really, okay? So you can't do that. When you have more bonds than you do atoms, then you have to start making multiple bonds, okay? So keep pushing that. So now we do that. Each bond has 2 electrons, so we have 6 shared. So we can check these off. All right, are we done yet? Okay, we still have to match up to our 10 valence. Okay, so we just go fill the octet. So we already have 6 around each nitrogen. So there's 8. And there's 8. And now we have a total of 10. Okay. All right, now I got to try to get back to why it does this. Okay, so those were diatomic molecules. We can have simple ones also where we have two different atoms. We have H and F, so there's only two atoms, so it's still pretty simple. Okay. We know hydrogen is always going to make one bond. Okay. And then fluorine, so some of these are pretty easy to do without even going through this, but it's best if you do, just in case. Something like N2, you might, mess up there if you don't. Okay, and so we check everything. So if we went through and I encourage you to do an ASB, we're about to do, some more practice, but you would find that you would need one bond, and then there's your 8. So you would have 8 valence electrons. So in your available column, you would get 8. Okay, so you can practice that one. We're going to go on to ones that are a little bit more difficult. Okay, here is water, which we already did. And I don't know why this database wanted to always draw that, but I prefer that you just draw the bonds instead of. Okay. All right, so we're going to do ammonia, NH3, and then show one that has a charge, so we can use that rule. Okay, so let's drive me nuts here. All right, I'm going to go to some blank paper here. Okay. So we're going to do NH3, these two. All right, so we write out NaSB. I don't know what just happened. It drives me crazy. Oh well, now I'm in red. Okay, so this is ammonia. All right, so let's add up the needed. Okay, how many electrons does nitrogen need? 8. Okay, how many electrons does hydrogen need? 2. And then how many of them do you have? So times 3. All right, so what does that give us? Available nitrogen is in group 5, so it has 5 valence. Hydrogen is in group 1, and we have 3 of them. So we get 8. Okay. If we take 14 minus 8 to get shared, we get 6. Okay, so how many bonds is that? 3. 6 divided by 2, there's 2 electrons in each bond, is 3 bonds. Okay, what's going to be our central atom, nitrogen or hydrogen? Yep, hydrogen's never in the middle. Okay, we have 3 bonds, and we have 3 hydrogens, so that works out good, right? We're just going to have single bonds because we have 3 hydrogens. So we can make 3 bonds. There's 1, 2, 3. Everybody agree so far? Okay, does my structure right now at least match up with what my formula says, NH3? Okay, so we made 3 bonds, 6 that were shared. Okay, how about available? Are we done? Okay, we need 2 more. All right, so who's going to get those 2 electrons? Nitrogen. Never, ever, ever, ever hydrogen. Okay, so we go to our central atom. And it may not seem like a big deal to show lone pairs or not, but this right here changes the whole reactivity of nitrogen, having that lone pair. It makes it a weak base. It makes it able to react. It's actually what we call a reactive site, a functional group. It can do acid-base chemistry. The lone pairs they pull very hard as well on your central atom. Okay, so they change the geometry. Okay, we'll get into that a little bit later. We'll do an activity with that. Okay, so they are very crucial to the structure of a molecule and the reactivity of it. So we won't get into all of that this semester, but they are very important. Okay, so this is called ammonium. It's a polyatomic ion that we'll look at later. Okay, we have an ion. So right away, which column are we going to have to adjust with because of that charge? The N, the A, the S, or the B? The A. Yep, we don't do anything to the needed. Okay, we still have one nitrogen that needs 8. Hydrogen needs 2, and we have 4. Okay, so that looks like that gives me what, 16? All right, available. Nitrogen has 5. Hydrogen is in group 1, and we have 4. Okay, if you forget to subtract an electron here, you're going to end up with an odd number. And what do you remember about odd numbers? That's not going to happen, right? Because we have to have even numbers because our bonds come in pairs, okay? So pairs of electrons. So we are going to add or subtract an electron here. Subtract, very good. So that gives us 9 minus 1 equals 8. 16 minus 8 is 8. And bonds would be 4. Okay, are we going to need multiple bonds here, do you think? Well, think about it. If you have 4 hydrogens, then you need 4 bonds, right? So you have to have single bonds because you have as many atoms as you do bonds. So okay, 4 bonds, 8 electrons. Okay. Can we check off our available? Do we have 8 represented? Yep. We count around 2, 4, 6, 8. The only thing left to do is you haven't quite represented this correctly unless you show that it's positively charged. Okay, because that's what our formula is, right? So we teach this a couple ways, but for you all, probably the easiest way, because it can get more, is just kind of put it in brackets and put that positive charge there. That tells you that whole molecule has a positive charge. All right, I want you to do this one, and then we'll go over it. SO3 2 minus. I'm about to move slides, so be sure you have that written down. I want you to also do NOCl. So nitrogen, oxygen, and chlorine. And we'll talk about that one a little bit. Give you a couple more minutes to try these, and then we'll talk about them. Okay, let's go ahead and do these. All right, we have no hydrogens in this one. We have 1 sulfur and 3 oxygens. So technically we have 4 atoms, right? And they all need 8 electrons. Okay, is everybody good with that? Did everybody get 32 for needed? Okay, so I'm just going to do, I need 8, and I have 4 atoms that all need 8. So get 32. All right, sulfur and oxygen are in the same group. Okay, everybody see that? Okay, they're in group 6. Okay, so technically here we could say that we need 6 times 4. Okay, that's the first part here. Okay. Let me check. Do what now? Yeah, let me show you. Am I going crazy? Or okay, make sure. I was like, I know they are. Okay. Yeah, so you have, they're in group 6. Okay. And so you have, well, I'll write it out better. That way nobody gets confused. Okay. We need 6 electrons, or we have available 6 electrons for 1 sulfur, okay? And then we have 3 oxygen atoms, so 3, well, that looks like 30, hang on. 3 oxygens, okay. And they also have 6 available. All right, we have a 2 negative charge, so we can't forget about that. We have to add 2 electrons here, right? Okay. All right. So we basically have 6 times 4 plus 2, so we should get 26. All right, did most of you get that far? Okay. All right, 32 minus 26 gives us 6 shared and 3 bonds. How about this far? Want to get this far? Okay. Which atom is least electronegative, sulfur or oxygen? Sulfur. So it's going to be central. So it's going to look like this. We need 3 bonds, and we have 3 oxygen atoms, so we're not going to need multiple bonds. Okay, so we've made our skeleton here, but now we need a lot more electrons, right? We've got 26. Okay, this is where that rule comes in to go fill your octets on the outside, on the skeleton first, and then go to the central if you have more. Okay, so we're going to go to our oxygens, and they need 6 more electrons. Okay. All right, how many electrons do I have represented now? 24, okay? Count around, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, but I need what? 26. So now I'm going to go to my sulfur atom, and it's going to have a lone pair. Okay, so then I put it in brackets because it has a 2 minus charge. Okay, questions? So a lot of people kind of back and forth. Questions? All right, if you look at NOCl, so we're doing this on purpose because there's really kind of 2 ways that you might think you could draw this one. Okay, first thing, what's the least electronegative atom? Okay, everybody agree with that? With nitrogen? Okay, so it's going to be central. That's a common mistake to accidentally not have it central. All right, we have a nitrogen, oxygen, and a chlorine, all that need how many electrons? 8. So we have 24 needed electrons. Available, same thing as valence. Okay, nitrogen is in group, what? 5. Oxygen's in group, and chlorine's a halide in group. Okay? All right, when you add those up, what do you get? 18? Okay. All right, 24 minus 18 is 6. So you get 3 bonds. Everybody with me there? Okay, I know that nitrogen is central, and I know that I'm bonded to an oxygen and bonded to a chlorine. Okay, so I just have 2 bonds. I can't make any more atoms, right? I can't just start drawing atoms off of it because then I change my formula. All right, so what's going to happen to get 3 bonds? Yeah, you're going to have to double bond. Okay, how many of you double bonded to the oxygen? Okay, how many of you double bonded to the chlorine? Nobody? Why? Do what? Okay, because it's a halogen. Okay. Technically, though, so yes, that's true, but sometimes there are exceptions there. Okay, but that is right. So I know that probably the best structure is going to be to double bond here. Okay, so then if I fill in 2, 4, 6, 8, and then fill in here. Okay. All right, how many electrons are represented now? 16. Does everybody see that? Okay, but I have how many? 18. Okay, so I'm going to need to go to my central atom and add what? Yep. Okay. This is the correct structure, okay, but I'm going to show you real quickly. Okay, one thing you can remember, like she said, is that halogens, so a chlorine, it's in group 7, right? So it just needs one more electron to be like the nearest noble gas. So most times, it really is just going to have a single bond. But you can also calculate this if you run into an error. So one of the worksheets I have on Blackboard, G is just like it, the bottom one, okay, where you have to decipher which side does the double bond go to. Okay, and basically, the idea, I don't know why it's doing this. Why is it doing this? Okay. You can calculate what's called formal charge. Basically, the idea is that whatever you have the lowest charge, whichever structure you draw, that's going to be the one that's favored, the one that's, more likely to be the structure. Okay, so we can actually go to all of our atoms and write in the formal charge. Okay, and so formal charge is the group number of that atom. So group number. Okay, and then minus the number of bonds plus unshared electrons. Okay, so just to show you why we picked the right structure, here it is. Okay. We know this one was the correct one. That's what everybody picked anyway. So, and if you were to look at each atom, okay, so if we look at the chlorine, it's in group 7. So that's our formula, is the group number. Okay, minus the number of bonds. Chlorine's making one bond, right? Plus the number of unshared electrons. So if you look at chlorine, it's got 2, 4, 6. So we get 7 minus 7 equals 0. So if you look here, we do that for every atom, we get 0 all the way across. Okay, that means this is the preferred structure because the charge is neutral. So typically the more stable an atom or a compound is, it's going to have a neutral charge or a lower charge. Okay, if you were to have drawn your bond the other way, to the chlorine, you would end up with charges. Even though the overall was neutral because you have +1 and -1, you would have charges on the oxygen and the chlorine if you do the formula there. So you can do that formula for each one. Typically, you really only have to do it for one of you could just do it for chlorine, and you would see that you would get 1 over here, and you would get 0 here. So that would be preferred. Okay, so we're going to let's do this one. Okay, we're going to do these two, and then you can get more practice. This sheet's great practice. You can go back into OWL. The ones I didn't grade, you can still go back in and do those. So it should still be open. If it's not, let me know. I've selected it to be open. So you can go back in and do those for practice. Okay, they won't be graded, but you can go in and practice them. All right, let's do these two real fast. And then I'll give you your exams. Okay. We have no hydrogens in either of these. so we're going to need 8 for all the atoms. Okay, so Dula, how many we're going to need for the first one? Okay, y'all listen up. We're almost done. Let's do these last 2. Okay, he said we need 24 electrons for needed. Everybody agree with that? Okay, yeah, 4 atoms, and they all need 8. So, wait a second. 8 times 4 is 32, so we need 32. Yeah. Y'all almost all agreed. Me too. Okay, available. Carbon's in group 4. Oxygen's in group. Chlorine's in group. And you have 2. Okay, so you have 14, 6. Is that 24? Okay. All right, 32 minus 24 is 8 and gives you 4 bonds. One of my tips was carbon is always in the middle. So, and it's the least electronegative. How convenient. So, here we go. Let's do this, this, and that. Okay, there's our skeleton. Okay. We can't mark off bonds, right? Because we've put in our atoms, but we only have 3 bonds. So we only had 3 other atoms to bond to, and we know we need 4. So this is where we run into an issue. Are we going to double bond here, here, or here? What do y'all think? Oxygen, yeah, because these halides we just saw, formal charge gets messed up then, right? We get a charge. So we're going to double bond to the oxygen, which is a very common functional group. And now we have to go around and fill in our exterior. Okay, don't forget when you have that double bond, it counts as 4. Okay, 2, 4, 6, 8. Don't put an extra lone pair on oxygen. Okay, carbon always wants to make 4 bonds. It is making 4, right? Okay, if you add up these, do we have 24 electrons? Yep, we got 8, 16, 24. Yeah, it's never going to have lone pairs. It's only make 4 bonds. Yeah. Yeah, you can't add any more to oxygen because it has 8. Yeah. All right, NO3 minus. We once again have 4 atoms that all need 8, so we have 32 electrons needed. Available, nitrogen's in group 5, oxygen in group 6. We have 3, and then we can't forget about what? Charge. We have a 1 charge, so we got to add an electron. And that's going to give us our even number anyways. So we add that up. What do we get there? 24. Okay, so same thing. We get 8 and 4. Okay. Nitrogen or oxygen in the middle? Nitrogen. There's our skeleton that matches our formula. Okay. Here we have all 3 oxygens around, so it does not matter which one you put the double bond to. You could do it to the one on the right, one on the top, or one on the left. It doesn't matter. It's the same structure. Okay, so I'm just going to pick this one. There's my 4th bond. Now I'll make 8 electrons around oxygen. I need 6 more here. And 6 more there. Okay. All right, how many electrons is that? 24, isn't it? So we got 8 over here, 8 on each oxygen, so that's 24, and that's what we needed. Okay, last thing though, what do we have to do? Put it in brackets and give it its charge. The whole day on Monday will be naming. This takes lots of practice. So there is a gigantic worksheet that I put on Blackboard, and you'll have naming on your OWL as well. But that gigantic naming worksheet, if you can do all those and you understand them, then you're good to go with respect to what will be on the test. So I advise you to do that. Now I'm going to give you back your exams. Don't forget that we have lab on Monday. Okay, I think we're actually doing 2 labs. You need to check your syllabus. Whichever ones are starred, you need to watch a video. Okay, so you need to look at that. Wear proper attire on Monday because we'll be going right after class to the lab. So I believe you guys make aspirin as well, so that's usually a pretty fun lab. So, all right, so let's give back exams. Let me stop this.